All right, we're going to continue looking at complex numbers, but we're going to look at them in a different way. We're going to try to look at this geometrically. So we had this number, 3 plus 2i. Let me rewrite that so it's a little clearer. 3 plus 2i. I can treat the real part like it's an x value, and I can treat the imaginary part like it's a y value. So I can think of this as 3, 2. So now that I can think of that as a coordinate. So this is like the real part is an x coordinate, the imaginary part is like a y component, or y part. So what does that mean? That means if I were to graph this, so again, we have z equals 3 plus 2i, we call that z1. If I take the real part as the x component and the imaginary part as the y component, I can think of this as a set of axes. So the horizontal axis is the real part, vertical axis is the imaginary part. I'm going to go over 1, 2, 3, because that's the real part, and then go up 2. So I can think of that point there as 3 plus 2i, or I can think of it as a vector, and that's my z1. Okay, if I think about it in these terms geometrically, I can take any imaginary number and write it like that, and I can think of it like a vector. And notice if it's a vector, then that means I can think of it as having a length and a direction. So if I'm given that z equals a plus bi, I would like to know what's the relationship between r and theta. Well, notice if I draw a vertical line there, I'm going to form a triangle. That's b and that's a. And so what do we have? We have then, and you can think of this as like a point on a circle of radius r. We have that r squared is a squared plus b squared, and we have the tangent of theta is rise over run, or b over a. Okay? So if I'm given a and b, I can use this information to figure out r and theta. Notice you have to be a little bit careful here. Right, you can't just use the arctangent because this could be in quadrants 2 or 3. So you need to be really careful how you interpret this. Likewise, if you're given r and theta, then a is just going to be r cosine theta, because it's this part of the triangle, and b is r sine theta, because it's the vertical part of that triangle. Okay, so for example, if I tell you z is minus 2 plus 2i, go minus 2 in the real direction, plus 2 in the imaginary direction. So I can think of z as looking like that. And then my r squared is going to be 2 squared plus 2 squared is 4 plus 4 is 8. By convention, we try to keep r positive, but sometimes that doesn't work. So r is the square root of 8. And the tangent of theta we know is going to be the rise over the run. Now, if I just take the arctangent, I'm going to get minus pi over 4. But I got to be careful here because I know that it's in the second quadrant. It's going to be pi over 2 plus pi over 4. So theta is 3 pi over 4. All right. Okay. One more thing here. What do we have? turns out there's yet another way to think about this. By the way, and the way we just looked at things is looking at it in terms of the polar form. Because if we know that A is r cosine theta and B is r sine theta, if I have a complex number, I can write it in that form. But I can also write it in that form. We're going to call this the rectangular form. And this we're going to refer to as the polar form. So you should be able to go back and forth between those two things. And there's going to be yet one more way, and that's going to be called the Euler form. So what's going on with that? Well, we defined I to be square root of minus 1. It's just some constant number. What does that mean? That means if I take the derivative of e to the it, since it's a constant, it's just going to be e to the it times the derivative of the exponent, which is going to be I, right? And that's because the derivative of it is just I times the derivative of t, which is 1. So that means if y prime equals iy, and y of 0 is 1, y equals e to the it is the solution. Right? And because we have an initial condition, that solution is unique. Right? And if I plug in t equals 0, I get e to the 0, so that's okay. I claim that y equals cosine t plus I sine t is a solution to the same differential equation. I claim it satisfies that differential equation. And we can easily verify this by just plugging into the left, plugging into the right, and see what happens. First of all, when t equals 0, we get cosine of 0 plus I sine of 0. Cosine of 0 is 1. Sine of 0 is 0. 0 times I is 0. So it satisfies the initial condition. Now if I take a derivative of cosine is minus sine of t, and that's I is a constant, so I don't worry about that. Derivative of sine is cosine of t. So on the left-hand side, I have sine of t plus I cosine of t. On the right-hand side, I'm going to have I times y. I just said y is cosine t plus I sine of t. If I distribute the I, I'm going to have I cosine t plus I squared sine of t. That's I times I, but I squared is minus 1. And that is exactly the same thing. So y of t equals cosine t plus I sine of t is also the solution to the differential equation. And the only way they can both be the solution to the differential equation is if this thing right here is equal to that. And that gives us Euler's formula that e to the it is cosine t plus I sine of t. And that's a really important formula, and you need to know that. Okay. So what does that have to do with Euler form for differential or for complex number? So again, we said the complex number is a plus bi, this rectangular form. Oops, I can write a as r cosine theta and b as r sine theta. Notice we just said that e to the it is cosine t plus I sine of t. If I replace t with theta, I get that. But now notice the real part is cosine theta. The imaginary part is sine theta. So if I multiply both sides by r, I get r cosine theta plus I r sine of theta, and that is the polar form. This is exactly equal to that. So we now have a plus bi is rectangular form is equal to r cosine theta plus I r sine of theta is the polar form. And I can write that as r times e to the I theta. And we are going to call that the Euler form. Those are all the same. So going back to our previous example, what did we had? We had z equals minus 2 plus 2i. We said r was square root of 8. Theta was 3 pi over 4. So I could write this as square root of 8 times cosine 3 pi over 4 plus I square root of 8 sine of 3 pi over 4. So that's the polar form. Equivalently, I could write it in Euler form is r square root of 8 times e to the I 3 pi over 4. Okay. Why is that nice? That is nice because suppose I tell you z cubed is 1. So solution is z equals 1. Turns out that's not the only solution. There's got to be 3 solutions to this. So how is that? Well, if I write z in Euler form, then z cubed is that thing cubed, and I can cube the individual pieces. But because that's an exponent, I can write that as e to the I 3 theta. So if I tell you z cubed equals 1, that's the same thing as saying r cubed e to the I 3 theta is equal to 1. Question now is what is 1? What if I wrote 1 in Euler form? What is 1? 1 is this number right there. All right, so if r equals 1 and theta equals 0, I get there. But notice there's another way to get there. Is if I were to go around one whole revolution, I could get r equals 1 and theta equals 2 pi. Could also go around 2 revolutions. So I can get r equals 1 again, but theta equals 4 pi. So that's 0, 1, or 2 revolutions. So what does that mean? That means then that I have 3 situations. For this case, I have r equals 1, theta equals 0. That's saying r cubed e to the 3 theta I is equal to 1. For this case, I have r cubed e to the 3 theta I. I'm going back to this here. Is radius 1, e to the I 2 pi. All right? If you plug into cosine 2 pi is 1, sine 2 pi is 0, you get exactly that. Or you can think of this geometrically as I start there and I do one whole revolution. And finally, I can go with this. All right, so my z cubed is that. And this is 1 e to the I 4 pi. And now I can work with each of these things separately. So here I'm going to work with the radius first. R cubed is 1. R, by definition, is a real number. So r equals 1 is the only solution. Then I have e to the 3 theta I is e to the, I'm going to write that as 0i. That's only true if the exponents are the same, so 3 theta equals 0, theta equals 0. So my first solution is 1 times e to the I 0, which is 1. What's going on here? Here I'm going to treat the radius the same, r cubed is 1. For the same argument, r equals 1. And now I'm going to treat the exponential the same. Those have to be equal. Those are only going to be true if the exponents are the same. So theta is 2 pi over 3. So my second solution is 1 times e to the I 2 pi over 3. And now over here, exact same argument. Treat the radii the same. R cubed is 1. Since it's real, r is 1. Now I'm going to treat the exponential. They have to be the same. Those are only going to be the same if the exponent's the same. So 3 theta equals 4 pi. Theta equals 4 pi over 3. So z3 equals 1 times e to the I 4 pi over 3. Okay, so if I try to find the roots of z cubed equals 1, there's 3 roots. 1, this thing, and that thing. Okay. Last thing, I want to do just a couple important notes about this. Notice from Euler's formula we had e to the I theta is cosine theta plus I sine theta. That means if I plug in, instead of theta, t, I'm going to get cosine t plus I sine of t. And that means if I have an expression or a function that has an exponential like that, what it really means is there's oscillations. So for example, if I have e to the I 3t, this is going to be cosine 3t plus I sine of 3t. And if I have e to the I 8t, this is going to be cosine of 8t plus I sine of 8t. So geometrically, I can interpret that as oscillations. Okay. Additionally, suppose I have e to the a plus bi. By the properties of exponentials, I can write that as e to the a times e to the bi, because that's just going to add those things. I can now use Euler's formula here. So e to the bi becomes cosine b plus I sine of b. So the real part is, when I multiply through, is e to the a times cosine b. The imaginary part is e to the a times sine of b. Okay, so that means if I have e to the a plus bi, the radius looks like e to the a, and then I'm going to have some kind of exponential thing there, or trig function going on there. So for example, suppose I have this function. I can multiply the t through and break that up into 2 exponentials. The real part I just leave alone. E to the 2it becomes cosine of 2t plus I sine of 2t. And I can multiply that through. And what does this have? So this is going to decay, because e to the minus 2t decays. And it's going to oscillate with a period of pi. How do I get that? So here's the thing. I've got cosine of 2t. As 2t goes from 0 to 2 pi, right, the thing I'm sticking into cosine is going to oscillate through one whole period. Right? And the reason for that is the cosine goes through one whole oscillation from 0 to 2 pi. So that means then, as you going back to here, divide through by 2, as t goes from 0 to pi, this is going to go through one whole cycle. Okay, so for example, e to the plus 3 plus 4it, can write this as e to the 3t plus 4it, and I can break this up into two pieces. So the imaginary, or the Euler part, looks like cosine of 4t plus I sine of 4t. This is going to grow exponentially like e to the 3t. And then I've got cosine of 4t. So as the argument goes between 0 and 2 pi, t is going to go, so I divide through by the 4. As t goes from 0 to pi over 4, it's going to go through one whole cycle. So the period is pi over 4.